When we talk about the AI revolution, one company is at the very center of it all, NVIDIA. Our next speaker is helping to build the brain behind the cars of the future. As the director of AI research at NVIDIA, his team is a part of the Spatial Intelligence Labs, bridging the gap between the deep learning and the physical world. His team isn't just building software, they are creating physical AI, foundation models, and self-evolving systems that allow autonomous vehicles to learn and adapt in real time. He's at the forefront of NVIDIA Drive revolution, and he is here today to show us how we are moving toward the world of safer intelligence. Please welcome José Álvarez.
Thank you. Thank you very much for the introduction, and thank you all for being here, for hosting me. This is a really wonderful event. So what I'm going to do today is talk about self-driving. And for those who don't know, I'm sure you all know, but the revolution is finally here, right? After many years trying, it has happened that over the last year and a half, 2 years, it's really, really easy to jump into a car that drives by itself. Let me give you a couple of examples. On the bottom right, there's a Tesla that you can buy, you can drive by yourself, and it can navigate really, really well on any complex situation. And then also on the top right, on the top left, we have a Waymo that also can serve as a robotaxi, where the only difference is basically the sensor suite. Tesla uses cameras, while Waymo uses more advanced sensors like LiDAR, radar, and whatnot. In any case, this is available today, and it's really easy to hop in and to test. On the NVIDIA side, we are also progressing really fast, as I will show you in the next slides. And the first thing that comes to my mind is asking you, how do these models learn? Do we know how these models learn? Are we aware? Please. Watching videos of cars driving. That's a good one. Now, what is next? What is missing, right? So if we really want to progress, what we really want to have is very safe and robust systems. So what we really want to ask ourselves is, how do we learn watching videos of something that did not go well? As we were hearing before, the systems learn by watching and repeating tasks, nominal driving, right? Things that we know how to do. Now, accidents, collisions, near collisions are really rare and are critical. So the question is, how do we learn with these events? The first thing that comes to our minds is the revolution of these end-to-end foundation models, right? These models can tackle everything. Just put data and go for it. Well, these models, the way we are training these models is basically collecting data, preparing the data, training the model. We evaluate, we make sure that it complies with what we want, and then we deploy the model. After testing and whatnot, we repeat the process again and again and again and deploy in an isolated manner. Here we have latest foundation models that include some reasoning capabilities. At the end of the day, not only output the trajectory that we want to follow, but also try to reason why that is a good idea. This is some work we did last year, and this is a more recent work, AlphaMayo R1, that NVIDIA has been promoting over the last few months, where it's showing that there's a situation and the model is able to reason, despite maybe not seeing that in the training data, they are able to reason and to get out of the distribution, right? What is the problem? These models tend to learn by mimicking what is in the data set, right? That's what is called imitation learning. And therefore, when there's a crash, when there's an accident, we don't have anything to imitate. If we imitate what is going to happen is that at the end of the day, we're going to teach our model to repeat the failure, and that's not acceptable. A common second option could be, why instead of collecting data, which in these situations can be critical and safety critical, why don't we generate the data? There has been a huge progress in data generation, as you can see here, where we can get an image and just change the weather, the conditions, the actors, and whatnot. Now the question is, what data should we generate? And the most important part is, can we really integrate this and make this data actually useful for training these foundation models? So the third option, which is complementary and I'm particularly interested, is the feedback loop. Instead of just collecting data, training the model, deploying, and repeat again, what we should do is close the loop. Once we deploy the model, try to collect as much feedback as possible from those models that are out there, and try to generate a training signal that is able to improve the data that we collect, and at the same time, improve the way we train the models. The more we do this, the better the models will get, the more users will be using these models, and the more we collect useful feedback that we can reiterate. And I want to make sure today that we understand this flywheel, this feedback loop, not as a data engine, but is an engine, is an operating system that is going to enable us to convert any driven mile, any driven kilometer into a signal that enables us to systematically improve our models. So what I'm going to do in the rest of the talk is talk about how we can generate these agentic flywheels. How can we automate this in a way that can automate the process of evolving the models, make them self-evolving, and try to convince you that at the end of the day, it might not be so much about who has the best model, but who has the flywheel that scales better, such that we can systematically improve faster our models to get to the end that we want. Before that, let me quickly go through my journey. Maybe some of you is interested. I grew up in Barcelona, in the neighbor country, Spain, and before joining NVIDIA, I've been wandering a little bit around the world, in Europe, in Spain, in Amsterdam. I did some work also in Germany, and then I moved to the United States, where I had the opportunity to work with Jan LeCun at NYU, and then I moved to Australia to also work on road assist understanding and bionic vision, and was fortunate to work with really good people, and then I landed at NVIDIA. It was funny because back in the days, I don't think now it matters, but back in the days it was like, why NVIDIA? And I think no one will ask that now. But the reason for joining NVIDIA back in the days was it was one of those places where you could work in the full stack. You can focus on the application, and at the same time go all the way to the hardware from the software. So it was a really good opportunity to try to be impactful with research on product. At NVIDIA, I started working on robustness, on efficiency, not only on the edge, but also how to train faster, how to train with less data, how to make things better and more cost-effective. Then we started applying those things to perception for autonomous driving. That turned to be the revolution of end-to-end systems. And more recently, now we are working on the full stack, not only on the end-to-end system, but how data and the model actually need to be optimized jointly, which is a very interesting journey, particularly for autonomous driving and physical AI. So let's go back to the flywheel and how to make these models evolve automatically. When we talk about the feedback loop, you might have heard about what I'm going to call the inner feedback loop, which is try to train or try to test your models using closed-loop evaluation. And this is possible these days thanks to data generation. We can reconstruct the scenes and we can modify how the agents interact. To some extent, we can now test our policies and see what the policy will see if it was tested in real life. But what is more interesting these days is the author feedback loop. What happens, not during development, not for the evaluation of the model, but what happens when we actually deploy the model. And the idea of the flywheel has 6 stages, right? Train, evaluate, and deploy does the same as before, but now what we want is to observe what the model is doing out in the world. We want to curate, try to understand what are those signals that these engagement signals that we are getting, observing, are meaningful, and how can we generate variations, or how can we generate a training signal that now we can include in our training process and systematically improve the model that we're going to deploy. Traditionally, this has been done very manually. If you think about a common process will be, you have users out there, you have the engineers testing the systems or whatnot, and they flag disengagement, they flag errors, they see errors, and they describe the errors. Then there's someone that tries to categorize, okay, this could be the severity of the error. Is it critical, is not critical, is just a false positive? What do we do with that? And then there will be another group of people that will try to understand what that error looks like and what will be the right data that matches that error. So as you can imagine, that doesn't really scale. So it's not really automatic. At the end of the day, we need a lot of people to make this happen. And if we think about a fleet of vehicles, millions of vehicles, that's not going to be possible, right? So we're going to be discarding data, and hopefully the wrong data is going to be discarded, which is not what we want. So with the new agents happening, we have the possibility to automate all this process, to use all these agents, all these foundation models specialized into AV, to try to automate the loop that we are talking about. And for that, instead of having people observing the data, we can have an agent that evaluates, an agent that categorizes the type of error, an agent that generates something that is similar to the error that we have seen, and another agent that says whether that generation is good and should be integrated into the training data, into the training cycle. More importantly, if each of these are agents, are automated models, then we can orchestrate everything, and we can have all these agents working for us while we do something else, right? So what I'm going to do today is going to very quickly walk you through, first, how do we actually should change the way we train our models to be able to ingest collisions and near collision data. And then I'm going to walk you through some work that we are doing on 3 of these agents: scorer, a curation, and a generation. Let's start with learning from collision data. As we were saying before, most of these physical systems, AV, is based on imitation learning, right? So at the end of the day, we need something that is good enough that we can imitate. If we have a near collision, a miss, a disengagement, that is a signal that we should not imitate. If we do it, it will go bad. So the question is, what other signal we can use during the training of our models? And the best way, and we have seen the previous presentation talking about RL, is try to generate a reward signal. So part of the work that we have been doing is can we understand the environment, and can we try to generate rules that allows us to create a score for each potential trajectory that says how good or how bad it will be, independently of having the human trajectory or not. For that, what we're going to do is try to perceive. We have really good perception systems, so we can understand how far we are from objects. Are we in lane? Are we deviating from the lane? Are we doing comfort ride? Are we being very uncomfortable? Are we braking? Are we accelerating? If we collect all these signals, we can try to understand this particular trajectory, how comfortable, how good it is. And that also means that we can generate negative rewards. If my trajectory is going to hit something, we can penalize that particular trajectory. So it's no longer imitate. Now we have a signal to not imitate, which is very powerful. The second challenge that we have with these foundation models is that if we only learn imitating the humans, what happens is that we are missing a huge portion of the action space. I'm quite sure if we all drive exactly the same situation, we will all drive properly and we will all drive differently, which means that there is more than one solution that the model should visit, right? So the way we're going to do that is, can we traverse all the possibilities that we have? And some people is trying to do that with diffusion models, multimodal models that output more than one trajectory. And in our case, we consider a dictionary of trajectories. We consider that instead of a continuous space in front of us, the car should only follow one of many trajectories possible in front of us. And so now that we have a reward, we can traverse all the trajectories and say, for this particular situation, which is the best trajectory? And we should follow that one. With those things, now we can train our policy, and we can include any type of signal, including collisions. We did some tests, and what you can see here is that it actually works. So the baseline is a baseline trained with imitation learning. And as you can see, the red is the ego vehicle, where we are applying our policy. And what it shows is that it's not able to react, and it crashes against the other vehicle. While if we train with this different reward, what we're going to see is that our policy is more defensive, so avoids the vehicle. Let's move on to the next part, which is how can we score? How can we know how good our policy is? And this goes back to the question of there is no single trajectory that is good. There's no single way of driving that is good. For a situation, there might be many, many, many things that we could do that will succeed to our goal of, let's say in this case, overtaking the bus. The way we evaluate the models in general is by imitation. So that means how close is our trajectory to one reference trajectory, which is the human trajectory. And that really doesn't work, right? So there's many more options that we could do, and it's well known that that score does not really correlate with how good the driving is in real world. The second could be, can we have humans scoring each of the trajectories, which one is good, which one is bad? And what happens with that one is that does not scale, right? So if we really have to, for every situation, have multiple humans scoring, that's not going to be a good solution. So the community has been working on this rule-based scoring, which at the end of the day, similar to the rewards that we were talking before, is if I understand the environment around me, I could sense how close I am to the objects. How am I deviating from my lane or whatsoever? So I can generate a score based on that. Now, the problem of this, while very powerful, is that the rules are meant to be broken, right? If you need to nudge, if you need to navigate around a vehicle, and you have a rule that says, do not cross a continuous line, that means that your car is going to be stuck there. While, as we can see in this example with some cones, common sense, any human will just navigate around independently of the lane markings, right? So we need something that is able to understand the context and break the rules when needed. And for that, these foundation models, these critiques are particularly useful. They understand the rules, and at the same time, with a VLM, what we can do is add the context of that particular situation. So we have been training these models to try to understand, with a VLM, can we understand the preference of the human driving? We have the set of rules, and at the same time, we have a set of trajectories that are the preference of a driver. We input that thing to the VLM, and we try to let the VLM score whether it's good or bad. And what we found out is that actually these VLMs as judge are really powerful to understand driving conditions. And what is more important is not only understand, but we can now assess how good and how aligned this driving is with the human style of driving. So now we know how good we are driving. That is great. Now we can, with that agent, we can score all possible disengagements. Is that a false positive? Is that a severe disengagement? Or VLM or agent can also reason and give us a why this is a critical event. And what we now the question is, what do we do with that, right? How, if we have a lot of data, can we traverse all that data? And what we find out is that the key is trying to organize this data. And we have seen in the last few years, again, because of foundation models, that training data needs to be organized. So now the question is, can we organize the training data and any other data that we have? And the way we have done that is grouping the data, right? And interestingly, what we can do is get one of these VLMs and ask, what do you see in this video? Give me the semantics, give me the situation. And it's going to describe each video clip with some sentence that is going to give us a very high-level understanding of the contents of the video. That was not possible before when we were using object detectors, we were using scene recognition. That was very narrow. While now what we have is a clear description of the semantics of the scene, including the actions on the scene. So here we have a couple of examples where we get all this data that we have available. We run a VLM asking, describe what you see. Describe, you're a perfect driver, describe what you see in front of you. And what we found out is that by clustering in the language space, we get very clear groups where data resembles something very specific. For instance, actions, cutting in front of the vehicle, or certain types of turns, or a pedestrian crossing in the street, which is very useful data. Now, it's much easier to select the data for training or to select the data that we want to fit into our model. We go to each of these clusters, and now we can select what is the most informative data within the cluster. We tried very quickly to see if this works, and what we did is, can we do it with the training data? Can we just break all the training data into clusters, describe them, and remove redundancies, remove data that is semantically similar? And what we found out is that with approximately 30% less data, we can achieve the same performance as with the entire data set. And what is more important is that if now we select data based on this organization, we constantly increase the performance. And at the end of the day, with the same budget, we get a significant boost in accuracy. Some people may think, is this relevant? Well, think about money, right? If training a model takes a few millions, more than just a few hours, right? If the cost of training a model is in the order of millions, now 30% is a significant budget that we would like to save. And let's go now for the last agent I want to talk to you about. Now we have data that is described. We have all our data somehow described and organized. But is that enough? Let's say we have a disengagement. We have something that went wrong. In this case, is our police is trying to make a right turn, and there's a pedestrian, and the policy doesn't see the pedestrian. Something went wrong, and we were about to run over the pedestrian. So we want to patch this situation. We want, in the next iteration, we want the model to do not make this mistake. So what we can do is describe as we have seen, and now just try to find similar scenarios. And we did that, and for example, we were trying to retrieve cut-ins, and we were trying to retrieve stop for turns and whatsoever. And what we find out is that we can actually patch errors. Give me an error, we will describe the error, and we will go one by one, and very quickly we will be reducing the error rate for my model. However, if we want to scale, now what we need to do is the description of the error, we're going to just cluster it again, and it's going to generate groups of errors that hopefully is going to, each group is going to contain the key essence of the true reason behind the error. And with that true reason, we hopefully will be able to generalize better. Here we have some examples where, again, we traverse the errors, we group them, and now we can cluster them. What we can also do is guide all the training data, use this to now attract training data to match this distribution of errors. If we do that properly, then our model systematically will improve very easily. Now, is this enough? Let's recap again, right? So we have a disengagement that says there's a pedestrian crossing. I'm describing this scenario, but I should not do this. What happens if we have not a disengagement, but a failure? The same as we were seeing before, right? There's a car that is not obeying the traffic signs, and we just run into the car. Let's try to see if we can describe what happened. In the case of the pedestrian crossing, we get the description we use in our agent, and what we observe is that it says there's an intersection and there's a pedestrian crossing. What information is missing here? Is the description correct? It's pretty good, right? More or less. Now, the problem is that the pedestrian crossing the street and the car appears to go down should not be there. We need actually right behaviors. We don't need appears to slow down. We need to slow down. That is what we want to imitate. Otherwise, we're going to mislead our model. We really want something that stops to let the pedestrian cross. Let me give you a more schematic example. We have that situation. Which A, B, or C is the right answer that we are looking for? I guess we all agree with C, right? What really matters here is not there's a pedestrian crossing, we should slow down. The pedestrian should be crossing exactly in front of the trajectory of the vehicle. So what we need is not correlation. There's a pedestrian crossing, I should slow down. What we need is causation. What we need is the pedestrian is exactly in front of my vehicle. And with that, what we can do is now collect the data that has similar scenario, but the right behavior. And to do this, we're going to ask the model to generate what is the less variation that we could have done to avoid the problem. If we can describe the problem, we should be also able to describe the minimum variation that will avoid the problem. And that is what we are going to use to mine data. Let's see this in practice. Again, this video that we have seen a few times. Let's ask about the description, and the description is pretty accurate. And then the agent also says there's a crash, and actually tells us why there is a crash, what has happened. Now, what we can also ask is, what could we have done to avoid this? And that is the counterfactual that is really valuable. Once we have that, we can input this into data generation modules that are going to generate the right behavior, the right scenario, with a variety of data that is going to be particularly useful for training our models. And here's one more example showing how this actually is very powerful. In this case, we are trying to enter the highway. There's this pickup truck in front of us that is having some interesting maneuvers. And at the end of the day, probably we were watching the cell phone or whatsoever, and things happen, right? Again, we can ask, what happened here? And our agent is really good at describing what happened and why there was an accident. Now, what is more important is that also describes what we could have done to avoid the accident. With all this information, now we can generate situations where there's a car in front of us that we should slow down. If we input this behavior into our training data, we're going to get the results that we're looking for. Does this really work? Can we actually put the data and the right data and make it work? So we have been working with variations on the sensor. If we want to be robust, one other thing that we need to is vary how we observe the scene in front of us. So what we have been doing is also generating changes, augmenting the training data that we have, and see how that impacts our policy. And what we observed is that if we do that, what we get is that our policy learns much better, is more robust, and actually takes advantage of the data that we are generating. So it's a very powerful way to do this. So in summary, I hope I've convinced you that the flywheel can be automated and is a very powerful way to self-reinforce, to self-evolve our models. At the end of the day, we can put our agents to work, and that's going to enable scalability of collecting feedback and making sure that each mile that we drive is turned into a signal that helps us improving our model systematically. We talk about safety. Safety is critical for autonomous driving, and I think in general for any physical AI system. And for that, what we need is to collect that data that is really scarce, really, really safety critical. And we need to be able to learn from that. All this is possible now because with the new generation of foundation models, reasoning models, they can really absorb a huge amount of data. So it's the right moment. To make sure that this data is actionable, first, we need to change the learning paradigm. We need to go beyond imitation learning. And probably we should work on ways to generate rewards that are beyond just imitating one single trajectory. And last but not least, make sure that you have a very powerful automated flywheel. I do believe that is the most important source for learning in your model. It's not just a data pipeline, but it's an ecosystem that is going to help you improve your model. And if you have the right agents, that's going to enable the scalability of this flywheel to unprecedented situations. And the use of foundation models and agents is reducing the dependency with the humans, which at the end of the day is what enables the scalability. And again, I do believe that it's not about the model, it's about the learning practices. With the proper flywheel in place, what you will achieve is a systematic improvement that will guarantee that you get to level 4 in this case for autonomous driving. But for any other model, deploy the model early and collect feedback and make sure that you actuate on that feedback. Thank you.
First of all, thank you for your lecture. So right now we're going to do a quick session of Q&As. So whoever have a question, please raise your hand. So could you please stand up for the question, please?
Thank you for that very illuminating talk. I would like to know if, and you mentioned that in the cars there's different trajectories that are good trajectories or different actions that are good actions. Is there a calculation as to what is the best action? And along with that, how is that calculation done? Because safety may be an issue where you might have a few people walking in front of the car, but there might be one passenger in the car. So is there a decision being made as to what safety decision should be made?
Let me see if I understand the question. So you're saying when we talk about safety and scoring the trajectories,
Yes.
Are we taking into account the type of risks?
Yes.
In the work that we are doing, we are not taking that into account. I don't think anyone should be taking that into account. In our case, it's always on the outside, on the environment, what do we see? And for the scene that you're describing will be, there's a pedestrian in front of me, and my rule or my judge says that for this type of driving that the policy that I have at the moment, I should stay far away. I should brake smoothly. I should brake abruptly, or I should get closer. In Europe, I think in general, we brake much closer than in the US. I do, at least. In the US, really, like, people stay far away. So I think that is the key point. I don't think any more than that.
Okay. Thank you.
Hey. Hey. Oh. Hey, thank you for the presentation. I would like to ask do you think you've solved the domain gap problem, meaning if with the neural rendering simulations like Gaussian splatting? I guess my question is, can you trust the synthetic data as much as you would trust real data with running the model on a real car? Thank you.
That's a very good question. I think that's one of the open questions that is not there. That's why generating data these days is good. Making that useful is more challenging, right? So there is some evidence that when there's no data, synthetic data is better than no data. Now, if you look at the flywheel, the way we can circumvent that problem is by augmenting existing data, which is better than generating data, right? So the way we are doing that in this particular work is we're going to find similar real data that resembles what we want. So at the end of the day, we are learning from real data. And with neural rendering, we can augment the conditions. That is much easier. And we have some work that shows that that is useful, rather than saying, out of the blue, give me some data. that is, the domain gap is still there. It's getting narrower, but it's still an open question.
Thank you.